So in review, midterm is just over 2 weeks away. You have a practice midterm, so I encourage you to download this, print it, test yourself, time yourself if you'd like to, give yourself 90 minutes. On the day of the midterm, we'll meet in here. Exam will start at 10:05 sharp. You'll have 90 minutes to take it. All right. Any other questions before we move on? Now, I told you guys at the end of last week, we didn't quite cover everything from our unit on chirality. There was one aspect that actually helps blend this next section pretty well. That is a concept called optical activity. Obviously, when you guys hear this term, you're thinking, what are you thinking? Rotation. I think I. Tell me why you think rotation.
I just remember learning that last week.
He did his homework. That's why he thinks rotation. If you don't think I, you might think light. Fiber optics run across the ocean floor, and we transmit light through it to have the internet, right? So light, eyes, optics, optical activity. Optical activity is it's an effect of chirality. So we say that chiral molecules are optically active. And achiral molecules are optically inactive. But now we have to define what it means to be optically active. And to actually demonstrate it better, I'd like to bring you to a video, and I will post this video with the lecture recordings so that you guys can go back and review it. To set ourselves up, we're not just going to look at any type of light. We're actually going to look at a specific type of light. We're going to look at plain polarized light. I feel like that word is that name is a little bit cluttered. There's a lot going on. You guys know that light is an interesting thing. It is oscillations in both the electric field and the magnetic field. And when light is emitted by an object, it's often emitted in all directions. So imagine light is the frisbee that you throw between yourself and your friend. Sometimes you throw a frisbee and it doesn't stay in one plane as it travels to your friend. Sometimes it moves around. But you could also throw a frisbee that is perpendicular to your chest, or you could throw the frisbee so that it's parallel to your chest, and you could throw that frisbee so that it's within every plane in between. Light often takes up all of those planes. You emit photons that are oscillating in all of those planes. What we want to do is weed out all of the planes of light except for one, so that this is a frisbee flying in just one plane. We don't want everything in between. We'll use some sort of optical filter to do that. Your polarized sunglasses help to weed out different planes of light. Some of you might even have polarized windshields. I can actually tell that my windshield is partially polarized when I have my polarized glasses. That's because at different angles, the amount of light that hits my eye is changing. I've got 2 optical filters going through this. So we would set up an instrument that has an optical filter, weeds out everything except for one plane. This plane polarized light passes through a sample then. And after passing through that sample, it reaches a detector at a different plane, a different angle. That light has been rotated. The sample is optically active in that it has changed the plane that this light is moving through. So you might say that the wind to your frisbee is similar to this optical activity. The wind helps to change the angle that your frisbee is moving at. If it's a windless day, your frisbee keeps moving straight. And this is really challenging to explain. I think we all know that light interacts with matter because light is electromagnetism and matter is made up of charged particles, the electro and the magnetic part of electromagnetism. We know that light sometimes does crazy things. You learned in Gen Chem that you can have light of a certain frequency eject electrons off of metal. This is why it's dangerous to put metal into microwaves, because you will start ejecting electrons off of that metal from the microwave electromagnetic radiation. You know that the pigments in your shirt interact with visible light, absorbing some of that light and enhancing the reflection of the other light. Chlorophyll, a green compound, absorbs red light so well that the green light that it reflects is basically enhanced. So all chlorophyll looks really green because it's interacting with red light. This plane polarized light is not going to be absorbed by the matter in any way, but you know that a chiral molecule has a specific orientation in space, similar to your hand. An achiral molecule does not have a specific orientation in space. Its mirror image is identical to itself. So the best way that I can explain why a chiral molecule rotates this plane polarized light is that the electromagnetic radiation is interacting with the electromagnetic components of the molecule, the whole molecule. And it's interacting with it in a specific orientation. It's being kind of pushed or pulled by the components of that molecule, and it's always being pushed or pulled in this same rotational direction. It's weird stuff. An achiral molecule has no effect. So we looked at molecules and said every chiral carbon will be described as R or S. Through a polarimeter, the instrument that we use to do this analysis, some chiral molecules are considered positive, meaning they rotate light to the right. And some molecules are labeled negative, meaning they rotate light to the left. Interestingly, you can't predict the direction of rotation just by looking at a molecule. You can't analyze the absolute configurations of the chiral carbons and predict whether it will rotate to the right or to the left. You have to experimentally determine it. But you can. You can look at a sample and say, in my polarimeter, it's rotating light to the right. It's rotating light to the left. And you can measure the extent to which it rotates. So every enantiomer, every chiral molecule rotates light an equal and opposite direction. I'm going to say it rotates light in equal and opposite amounts. Now, this is not something that I'm asking you to predict because, again, we would need to have experimental data to look at it. So let's just take a hypothetical. Let's look at R2-bromobutane and S2-bromobutane. Let's make up numbers just for the sake of simplicity. Again, there is no relationship between R and S with positive and negative. They are related in the same way that R meant good and rotated clockwise, S meant bad and rotated counterclockwise. They were given the Latin words for that. Positive means rotates clockwise, light. Negative means rotates counterclockwise. But there is not a direct relationship between the absolute configuration and the direction. So remove that bias if you have it. Let's say that this light is rotated. We'll use alpha for rotation by plus 15 degrees. How much will its enantiomer rotate? Negative 15 degrees. They rotate light equal and opposite amounts. Now let's look at a different set of molecules. Let's see, this is 2R, 3S, 2,3 dibromohexane, and then 2R, 3R, 2,3 dibromohexane. What's their relationship? These are diastereomers. Good. Are they going to rotate light equal and opposite amounts? Let's put a value up here. Let's say that the rotation for this compound on the left is negative 32 degrees. Can we predict the rotation of this diastereomer? They have no optical relationship to each other. So here's what I would want you to take away from this. Diastereomers, we'll say, are not optically related. I'm sorry for making up numbers. I could have come more prepared with real molecules. So if you want to see how this applies to real molecules, I encourage you to go do some research. We're just picking really nice numbers here. We'll say that the rotation of this diastereomer is negative 2 degrees. Why? Because they are not related to each other. That's all we're getting at here. And then lastly, achiral and meso compounds, again, no rotation. But then we get to this term of racemic mixtures. The name here, racemic, is fairly interesting. It actually is derived from the two enantiomers that first presented optical activity and chirality. I believe it was to Louis Pasteur, who invented the Pasteur pipette. You guys in lab are using those glass pipettes. Those are considered Pasteur pipettes. He also was pretty instrumental in vaccinations and pasteurization. Maybe not vaccinations. I think that's right. Anyways, he was looking at racemic acid. And he noticed that crystals of racemic acid would grow in different spiral conformations. And then he selected out those crystals and found that they were stereoisomers of each other. They were enantiomers. So he coined this term racemic mixtures. So racemic acid has since been renamed because racemic has now been taken by this term. Racemic mixtures are 50-50 mixtures of enantiomers. So going back to this idea of R2-bromobutane and S2-bromobutane, what if I had a sample that I put into my polarimeter that had 50% of each of them? How much would the light rotate? They counteract each other. As it passes one molecule, the light gets rotated 15 degrees clockwise. Passes the other molecule 15 degrees counterclockwise, net 0 rotation. There is an interesting thing. There's a lot more math involved in it. We're not going to get into it much. I'm just going to show you that it exists. And that is the idea of enantiomeric excess, which says if you have one enantiomer present more than the other enantiomer, let's say 3/4 of your sample is R, 1/4 of your sample is S. Then you can do some math. We're not doing too much math in our class. You can do some math, and the rotation will be the result of that percent of the enantiomer that is in excess. So basically, 50% of your sample is R, and the other 50% is a racemic mixture. The 25% of S cancels out 25% of the R, and the 50% of your sample that is excess R rotates light in that direction. So we can say that this rotates light 7.5 degrees. If it was pure R, it would have rotated the light 15 degrees. But really, it's like a 50% sample of R. So it doesn't rotate light as much as you would think. Interesting. So we can actually take a sample, analyze its rotation of light, and figure out how much of one of those enantiomers is present. There's one other term I want to put on the board. I'm not going to give an example with it. If you don't have an enantiomeric mixture, or a racemic mixture, then that means you have a mixture of diastereomers, and we call that a diastereomeric mixture. I just like that word a lot. I think it's fun to say. And we'll talk about diastereomeric mixtures after the midterm when we start looking at reactions. So I want you to see the word now because it's going to come back. And it's not a weird word. It just means a mixture with diastereomers in it. If you took these two compounds and mixed them together, you'd have a diastereomeric mixture. All right.
the diastereomers, you said the name was like 2R2S.
2R3S.
Oh, okay.
Yeah, so this carbon is R.
Yes.
This carbon is. Oh no, this carbon is also R.
So 2R3S?
1, 2, 3. Yeah, 2R3R.
Okay.
2R3S.
So it's just like locant of where the chiral center is.
Yes.
Okay.
Yes, exactly. I think we looked at that last week. We had a molecule on the board and we called it 1R2S 1,2 diabernyl cyclobutane.
Okay.
And then we looked at its diastereomer, the 1R2R 1,2 diabernyl cyclobutane. So we can put locant with absolute configuration into the nomenclature.
So when we're talking about light coming at a molecule and its chirality affecting how that light reacts,
How that light moves through space, yep.
are we talking about the same thing as refraction, or is this different than that? Like light hits it and then it does this versus doing this? Or is
Good
that
question.
A completely different concept.
So refraction causes the sky to be blue. Refraction and scattering, I want to say those are pretty much equivalent things. The longer the wavelength, the less light scatters or refracts off of something. The shorter the wavelength, the more it refracts. That's why blue light scatters the most in our atmosphere and we see blue. And then at sunset, the sun is pointing straight at you and all of that red, orange light passes straight through the atmosphere and hits you. This is not refraction. If it was refraction, you might not get the sample, you might not get the light at the detector. So the light is passing straight through the sample without refracting. But it's changing the plane that it's traveling in.
Okay.
I gave that analogy with a frisbee. You throw it horizontal, and if it reaches your friend vertical, it has rotated its plane. And something must have caused that. The frisbee is a bad analogy because obviously I throw it a little bit differently. I'm going to put some spin to it. But you can see the relationship there, right?
So change in plane, not the same as refraction.
Not the same as refraction.
Change in plane is what we're talking about here when it comes to chirality.
That's right.
Right versus left has a different effect on your plane when light hits it. Potentially.
Right versus left. Are you saying positive and negative?
I guess so. Yeah.
Um,
I guess what I'm saying is like light hits it, and whether or not something is chiral, the result is different based on
what
whether
its
it-
chirality is.
what its chirality is.
Yeah. But we will not be able to say, well, we can determine the absolute configurations, but we cannot relate the absolute configuration to the direction that it rotates light. So you might see compounds out there that are labeled plus menthol and minus menthol. Those are very common. But you don't see the absolute configuration listed with the name. You could, as an alternative, but you don't. So we are talking about a chiral molecule interacting with a plane of light, not all light, not light like this. One plane of light and causing that light to change its orientation in space, to change its plane.
So, you had talked about how, like, with enantiomers, they can have a really different effect, like, in the body. For
Yeah.
example. But that wouldn't be the case with optical activity. Like,
That's right. And that's because in biochemistry, a lot of your enzymes are also chiral.
Oh, yeah. Okay.
So this is like how your left hand only fits in a left-handed glove. That's chirality in practice with biochemistry.
Mm-hmm.
But if you put your two hands into a light and the shadow on the floor was rotated clockwise for one of them and counterclockwise for the other one, That's optical activity, which would be a weird thing. But light is weird, so maybe it would happen. All right, let's take a look at this video on light.
A laptop with the screen down, the yellow field in the background. Also a pair of polarized sunglasses, and there's a can that's glued to a small pane of glass. Inside the can is some glucose solution, it's actually Caro syrup, and the screen is polarized light. So when I bring out this polarized sunglasses, you can see that there's if I twist here, I can block the light. The screen for the laptop is actually polarized at a 45-degree angle. If I twist at that angle, I can block the light. You'll notice that the light coming through the glucose solution is a different angle of polarization than the screen itself. If I rotate here 25 degrees this way, I get light there.
So I just want to clarify what's happening. He's got a sample with sugar, chiral or achiral. Kind of looks like there might be a plane of symmetry here because these dashed alcohols reflect. But then I've got an alcohol and I've got a CH2OH. Those do not reflect to each other. So this sugar molecule he's looking through is chiral. He's got his laptop screen, which is only emitting light in one plane. He's already got plane polarized light. Then he's got his sunglasses, his polarized sunglasses, with his camera looking through them. Which means if the plane of light from the laptop is perpendicular to the plane that can come through his sunglasses, he'll see nothing. But if the plane from the laptop is parallel to the plane that his sunglasses allow, he'll see light. And you can see that in the in-between angles, it gets lighter and darker. But when his sunglasses are blocking light from the laptop, it sees light from the sugar because the sugar is rotating light that is passing through it.
Because the light coming through the glucose.
Notice when he removes his sunglasses, you can't see the difference. The sunglasses are a polarized filter.
Light is coming in.
Here, he's got 4 different solutions. One is water. How will water affect this plane polarized light? It will not rotate light because water is achiral. So he's got a sample of water. That's a control. So when the screen goes dark, the water should go dark. Then from 1 to 3, he's got different amounts of that sugar solution, meaning the light will have to travel through more of that sugar the more there is, which means the light is going to rotate more the more sugar there is. His wife also shows up in this one, which is very wholesome.
And then 1, 2, and 3 are increasing amounts of glucose, so Caro syrup, and then sunglasses over it. Kathy, can you spin that for me just real slowly? The background is yellow from PowerPoint with an arrow looking at the angle here. I think with the idea is maybe later on you could print these out as pictures and then look at the angle and compare that to the amount of light coming through. See, number 3, which has the most glucose in it, is now dark. And the W is for water. 2 is now getting dark. And 3 is lighting up, and there's 1 now is going dark. Now the screen itself is going black. The screen is polarized at a 45-degree angle. Now we've gone halfway around. Yeah, he's doing a real nice job spinning over there. 3's darkening up again.
For you or someone else.
This has been on YouTube. And 3's dark again.
Number of hits, 2 from David White and Cynthia White.
Can I go back a little bit? Yeah, go back a little bit more. A little bit more. Okay, keep on going. Now screw yourself dark there. And then we're right back where we started. Very good. So now you can analyze the angle of polarization based on darkening and lightening there, different concentrations, different amounts of syrup there.
Number of hits, I think is more than 2 now. Because I show this every semester. How do you see the number of views? Anyways, what do you guys think of that video? Trippy, how light? 13,000? Where do you see that? Oh, right there. Yeah, Cynthia thought it was only going to get 2 views from the 2 of them. And it's not me having all 13,000, let me tell you. Okay.
So if it's the same molecule that we know has a given angle of that it changes the light, why does the different concentration change that?
Actually, in this math, and don't let anybody tell you that organic chemistry doesn't have math. You're just not going to be tested on the math. In this math, the path length matters.
So it is it's a mix of the two.
Mm-hmm. So I gave you these numbers here. We would have to say that the same path length was applied here as well. If the light is leaving the light source, hitting the detector, and moving 10 decimeters, so 100 centimeters, and then I keep that standardized, and I change the ratios of my solutions, then all of my math stays consistent.
So it's degrees of rotation per distance.
Yeah. Mm-hmm. We can even report standard rotation, which means that we make it per path length, per concentration as well. So if I have a more concentrated sample, then there is more of that compound to interact with the light, and it will rotate the light more. If I have a longer path length, then the light has to travel through more of that sample before it hits the detector, and it will rotate more. So actually, these are very similar to Beer's law. Do you guys remember learning about this in general chemistry? Absorbance is equal to the molar absorptivity times the concentration times the path length. Did anybody not learn Beer's law? Interesting. Okay. Yeah, I know that I don't teach it in Gen Chem 1, so I'm curious if you guys saw it in Gen Chem 2.
Would a different color of light affect the angles of the polarization?
Maybe, yeah. I'm actually not quite sure. Polarimeters, I think, do use a standard wavelength of light to avoid scattering, to avoid absorption. We don't want that light to be absorbed by the compound. So I think there is a standard wavelength that is pretty more or less inert.
You can put on a different light sources, the different light sources change the angles.
I don't know that it would change the angles, but what I would be more worried about is that it doesn't pass straight through the sample in the same ways. That some of that light becomes absorbed by the molecule, or that it refracts more. I think it doesn't hit the detector quite as well. We could look into it more, but I'm not sure. So, concentration matters, length matters, because the light is constantly interacting with the sample. So the more it has to go through, the longer it has to go through, the more it changes. All right, I want to give you guys a quick break, so why don't we take about 5 minutes. You can stand up, move around, get your blood flowing, and we will dive into our next type of instrumentation.
So just to make sure I was understanding correctly, so this one rotates 75 degrees, this one goes back 25.
Well, I think we said this one rotates 15 degrees clockwise. This one rotates 15 degrees counterclockwise. So 25% of my sample is rotating the light 15 degrees counterclockwise and canceling out 25% of this sample.
So you're like with 50%, and then you just take 50% of 15.
Yeah, but you know, like that math is a little bit weird. So I maybe could have just cut it short by saying it will be a positive rotation.
Okay.
But it's not likely to be the full 15%. Because remember, concentration matters. And I don't have a 100% concentrated sample like this anymore. So for the same path length, I have a smaller concentration, I'll see a smaller rotation.
Okay, gotcha. Yeah, I thought it was just like, you get the percentage from this, like 50, and then find, since this one is a greater excess.
Yes. Yep.
This.
I haven't looked at the equation in a long time. I think it is something like that.
Okay, because
We call it the enantiomeric excess is 50%.
yeah.
And then you take that enantiomeric excess and you multiply it by
So
its rotation.
on like a test or something, like would this be like a given?
If necessary.
Okay.
Yep. The way that I typically have this show up, you'll have a question on, will this compound rotate optical light or not? And then that's just a matter of, is it chiral or not? Is it a racemic mixture or not? The other way that I like to show this, I'll have bonus problems that show a reaction, and then we'll get a bunch of data about the starting material and the product. So we can say something like the rotation of the starting material was 0 degrees, but the rotation of the product was plus 15 degrees. In no way do I expect the direction or the amount of rotation to tell you anything. But the fact that it rotates tells you that it's chiral. That's it.
Okay, so it was an achiral and like racemic don't rotate.
Yeah.
And then dash, we didn't really go much.
They will rotate, but not really in a predictable way, because they're not always related to one another.
So we just need to like and American excess.
Yep, exactly.
So I went and did shadowing in the mycology and I swear they were showing me a machinery that all the it kind of does a similar thing because it was taking this, you put like a little tiny bit of a sample on a plate, and then you put the plate in the machine, it fires like lasers at specific spots, and then they can tell based off of like the response and the shapes, like kind of like get a general idea. It's probably going to be like Staph aureus or something. Kind of seems like it's almost doing the same thing.
So a MALDI is a matrix-assisted laser desorption ionization instrument.
Yeah.
But this says that it's a mass spectrometer, and that is the next type of instrument we're going to look at next.
Okay.
So I don't think it uses
This.
chirality.
I
But
just
it-
was thinking more the fact of light.
Yeah.
Maybe
Actually,
not actually. But
we're going to look at
something
three
about the
instruments.
shape. They were saying like the distinctive shapes, and then the fact that they have like huge database and stuff.
Mhm.
So
There are 3 instruments we're going to cover. 2 of them use light. The last one uses magnets. But it's crazy how widely light can vary and how its
They can't.
properties can vary because of that.
Yeah, I was reading the beginning of the chapter when I was at work
I
last night.
forgot they have them behind the counter, so I forgot to ask every time I checked.
You have a huge mass spec lab.
Do you?
Oh yeah.
Mass spec, in my opinion, is the most useful with a giant database. When it was developed, people had to figure out how to interpret the information. But now, I can just put a molecule in, check it against the database, and the database says it matches this compound.
yeah.
That's your compound.
They've actually, our lab, or I mean, our company has started venturing into that text site. Is I think what it's called, but it's doing kind of the same thing where they're plugging the information in for like, I think it's our IDAT and our parasitology labs. And so it'll be like, hey, this might be a positive, but like it's kind of doing the same thing where they're using like AI to help narrow down like, and instead of one person looking at every single thing, AI is being like, hey, this might be something. Because there's so much.
Interesting.
Yeah, it was so cool. I got to go through the BSL 3 lab. Double doors, you know, negative pressure.
That's great.
Testing aspergillosis, tuberculosis, and that's
Really? Just from farming? Yeah. From barn? You can't get too far. Really? Maybe I'll check Jordan. Yeah, that's near my house. I got it's your info, dude. If I see it, I'll let you know. You guys captured it? Yes. It's just not so good.
All right, now I'm putting some things up on the board that might feel far from where we are right now, but in reality, we're getting towards 3 weeks away from learning about this. But I want to ask you questions about optical activity in regard to this. These are organic reactions. You can see that in both of them, I've taken a starting material that has an alkene functional group, and I've consumed that alkene. I've done a reaction that means there is no alkene left. In the first one, I react with elemental bromine, and I create a dibromo compound. In the second one, I react with elemental bromine in the presence of water, and I make an alkyl halide and an alcohol compound. So here's my question. Which of these compounds, starting materials and products, will rotate plane polarized light? Which of these compounds are optically active? And which of these are optically inactive? Talk to me about the first one on the top left. Optically active? I'm getting different things. You want to tell me why you think it's optically active?
I just split it horizontally and reflects, and they're both wedges, so I think it's active.
There's no wedges. Sorry.
I was talking about the product.
Oh, okay. Sorry, let's start with the starting material. Optically active? No, it is achiral. So this will have no rotation. Now you said you split it this way, and there was no reflection?
I just like it was...
no symmetry.
Yeah.
Now remember, a molecule only needs to have a plane of symmetry in at least one of its conformations to be considered to have a plane of symmetry. So it might be useful for me to think of this in a different conformation to understand whether it has a plane of symmetry. We actually looked at this one last Thursday. We looked at this molecule and a diastereomer of it. And we said that even in a different conformation, there is no plane of symmetry. Now here's the challenging part about this reaction. I'm going to add a little bit of information to it. The product would be labeled as racemic. Even if they drew just one enantiomer, we can say that the product itself is racemic. What does that mean? It means this enantiomer forms, and where the two chiral centers change configuration, also forms 50-50. So will that racemic mixture rotate plane polarized light? No. So the challenging thing in using polarimetry here is that it doesn't necessarily tell you whether you formed an achiral or meso compound or whether you formed a racemic mixture. What about this compound here? Will this rotate light? Is it chiral? Yes, it is. This methyl group, it does not have two identical sides. No plane of symmetry cuts through this. Now, I don't know what its rotation will be, but it'll be plus or minus something. Let's say plus or minus x. What do you notice about the products? Two products form. How are they related? They're diastereomers to each other. The methyl group has the same configuration. One chiral center conserved. The alcohol has different configurations. One chiral center flips. And notice that the bromine is not on a chiral center. So it doesn't really matter whether we show it as wedged or dashed. So will this have rotation? Is this a racemic mixture? No, it's not a mixture of enantiomers, which means that it's not going to have an equal and opposite effect on the light. So this will rotate light, but plus or minus some other amount. So I'll say plus or minus y. Doesn't necessarily tell me that I make a diastereomeric mixture, but it does tell me that I have at least some amount of chiral products. Polarimetry can be useful, not the most useful. On some of your midterm exam questions where you see polarimetry come up, it'll be mostly, is this compound optically active or is this compound optically inactive? But in the second half of the semester, I like to give you data about reactions. And one of those pieces of data I can give you is polarimetry. But sometimes it's not that meaningful because you can't flesh out whether it's a diastereomeric mixture or one enantiomer, or whether it's achiral or a racemic mixture.
Yeah, I'm just curious how, like, in both of those reactions, how you know where to put the bromine in the water.
Yeah, that's called regiochemistry. You'll notice I put the bromine in the same spot and the alcohol in the same spot. The bromine went to the less substituted carbon. The alcohol went to the more substituted carbon. And we're going to talk about that regiochemistry when we look at those reactions.
It's basically like substitution order.
No, it's not about priority of the substituent. It's about reactivity. We're going to look at both of those reactions this semester. And we're going to say, we're going to look at the mechanism. So we'll explain how the bonds break, how the bonds form, what sequence they do them in, and how many steps are required for the reaction to be completed. For instance, I'm showing you this reaction across one arrow, but this does not happen in one step of breaking bonds and forming bonds. It actually requires 3 steps. Breaking bonds, forming bonds, breaking bonds, forming bonds, breaking bonds, forming bonds. And we'll learn those mechanisms in the second half of the semester. Right now, though, just an application of optical activity towards real life, towards synthesis reactions. All right. That was a segue for us from Unit 2 to Unit 3. Unit 3 is on spectroscopy. We're breaking spectroscopy up into 2 sections, one of them on IR and NMR, one on IR and mass spec, the other section on NMR. We're going to explain what those acronyms mean. Spectroscopy, though, it's actually a little bit easier to explain than you might expect. This is really just creating spectra. It's creating a spectrum from analyzing a molecule. First, let's do an overview of our three types of instrumentation. In this word, again, you hear spectrum from that spectro part, and you hear metry, so that's measurement. This is measuring a spectrum of mass. One of the most useful things that mass spectra give us if you have an unknown compound, mass spec can give you the molecular mass of your compound. Does molecular mass give you the chemical formula? Not always. Many compounds have the same chemical formula, many compounds have the same molecular mass, but different chemical formulas. So it's one step towards understanding your compound better. The other thing that it can give you are these molecular fragments, which can actually give you a better picture of how your molecule is structured. And it gives you just the mass of those fragments, but having smaller pieces of your molecule laid out to you can help explain how your molecule is connected, can help explain different groups in your molecule. We call this mass spec. IR, its full name is infrared absorption spectrometry. Again, measuring a spectrum of absorption in the infrared region of light. Do you guys know what infrared light is otherwise known as? Anybody heard of infrared cameras? What do those infrared cameras help you see? They help you see heat. So you can also call an infrared camera a heat camera, or a night vision goggles, heat-seeking things. They look for infrared light. So infrared light, IR light, is heat. When you stand in front of a fire, you're seeing a lot of light come off of it. You're also feeling a lot of heat. Some of that heat is literally just kinetic motion, hot things moving fast. Some of it is electromagnetic radiation in the form of infrared light. The Earth emits infrared radiation, mostly at night, takes in a lot of energy from the sun, changes that energy in different ways, and radiates it from a lower frequency, lower energy, longer wavelength, and emits infrared light. That infrared light actually gets absorbed by carbon dioxide, methane, and more than either of those, water. When volcanoes erupt, they throw tons of water into the atmosphere. That water absorbs infrared light that's emitting off of the planet, keeps the heat inside of the planet, adds to global warming. So the more we increase CO2, the more we increase methane, the more we increase water in the atmosphere, the more the atmosphere can hold on to heat by absorbing infrared light. Do you guys know what heat is, though? Yeah, heat is energy motion. I see tumbling signs. In general chemistry, I taught you that, I didn't teach you guys, that's why I pointed out that. In Gen Chem, I taught you that heat is actually transfer of energy, heat flow. The heat death of the universe is when there is no more energy being transferred. It's when heat stops. It's when energy flow stops. So when we say that infrared is heat, and heat is the transfer of energy, we're getting terms kind of crossed. So the way I'd like you to think about this is that IR light can give energy to molecules and heat them up, give them more motion, give them more energy. The way that it does that is by making the bonds stretch more and making the bonds bend. That's how it gives energy to it. It's not kicking them along, giving them energy. It's giving energy to their bonds. IR absorption spectrometry. It gives us bond types because different bonds will absorb different frequencies of infrared energy. The energy that it takes to stretch an OH bond is not the same energy that it takes to stretch a CH bond. The energy that it takes to stretch an sp2 hybridized CH bond is not the same as the energy it takes to stretch an sp3 CH bond. So different bond types determine the energy that is absorbed in the infrared region. So we look at an entire spectrum of infrared light, not just one frequency, but many frequencies. And we see what frequencies get absorbed. And not every bond type absorbs its specific energy well. So we get some bonds that absorb very strongly, some bonds that absorb very weakly, and we get an infrared spectrum that has deep peaks, shallow peaks, wide peaks, narrow peaks. We're going to learn how to analyze that spectrum to tell us what bond types are present. Our last one is nuclear magnetic resonance, otherwise called NMR. Have any of you ever been inside of an NMR? Sorry. Have any of you ever been inside of an MRI? A few of you. That means that you have been inside of an NMR. You have been inside of a human scale NMR. You were the analyte. You were the compound being analyzed by the MRI, the NMR. The only reason that we don't call MRIs NMRIs is because no one wants to climb inside of a giant tube that clunks really loud, whose name starts with nuclear. But it is the exact same principle. It is the exact same science. NMRs were adapted to be used in medicine, which was a great use. NMRs obviously don't look at an entire mass of a molecule or the mass of an entire fragment. They don't look at the bonds that are present. They look at the nuclei that are present. And we're going to focus in on just one type of NMR. There is another type of NMR that is a little less common. I'll mention it. But we're going to focus on proton NMR, H1 NMR, the nucleus of the hydrogen atom. NMR is going to tell us how all of the nuclei of the hydrogen atoms are connected in a molecule. This gives us structural connectivity. And I don't know if you guys have noticed, but structural connectivity is not a trivial thing. Even with the molecules that are on the board right now, we're going to look at an instrument that will tell us how all of those hydrogens are connected to those molecules. which is kind of wild. NMR actually uses a magnet. You take a sample, you put it inside of a magnet, and that magnet then orients all of the spin of the nuclei. Remember, magnets and charged particles, they go hand in hand. And we will orient the spin of all of those charged nuclei in the same direction. Except there are other charged particles besides nuclei. Electrons are charged particles that can be interacted with the magnet as well. So if a nucleus has a lot of electron density around it, we say that that nucleus is shielded from the magnet. But if a nucleus has its electron density pulled away from it, then we say that that nucleus is de-shielded. So not every nucleus interacts with the magnet the same. And then those nuclei relax down to a ground state, and in doing so, they emit electromagnetic radiation in the radio wave frequency. So the NMR listens for radio waves. Well, it's light, so it looks for radio waves. And it interprets those radio waves and explains all of the different properties of the nuclei inside of that system. We can also apply NMR to fluorine-19 protons, or nuclei. We can apply this to oxygen. We can apply it to carbon-13. We'll talk briefly about carbon-13. It's much harder to do. It's very expensive. Proton NMR is very easy to do. It's much less expensive. So proton NMR is our main focus. By coupling all of these pieces of information together, you will be able to take a chemical formula and figure out what that molecule is. I gave you a chemical formula on your unit test this weekend and had you come up with a molecule. Make it fit this criteria. But by the end of this unit, I will give you a chemical formula and you will use information to decide exactly what structural isomer you have from that chemical formula. In order to do this, there is something very useful, and this is where I'd like to start or end our lecture today. There's one thing that we can get from the chemical formula that doesn't require any instrumentation. And that is degrees of unsaturation. A degree of unsaturation informs you about how many other atoms could be added to your molecule. It tells you how many times atoms within your molecule kind of double up on each other. So here's how I like to demonstrate this. We're going to look at propane. And we're going to look at a very specific orientation of propane, where I've got two hydrogens kind of pointed down. If I removed those two hydrogens and instead bonded those carbons to one another, would you agree that I have lost two hydrogens in forming cyclopropane? This ring structure unsaturates the molecule. It could be more saturated. There could be more atoms in the molecule, but instead, two of the carbons bond to each other to create a ring. So they have removed their ability to be fully saturated with unique atoms. There's another way that we could do this, which would be to take these two hydrogens and form a double bond. In either case, I'm losing two hydrogens. in order to create this pi bond or to create this ring. And you'd agree that the chemical formulas are different. C3H8. These two are C3H6. So there's two ways to do this. You can look at a structure and you can count the pi bonds and the rings, or you can plug in this equation. I call this equation the two chicken rule. I call it this because there are twos all over the place. There are two subtractions, and there are two additions, and it spells chicken. If you take twice the number of carbons, subtract the number of hydrogens, subtract any halogens, add the number of nitrogens, add 2, and divide it all by 2. So you multiply by 2, you add by 2. You subtract twice, you add twice, you divide by 2. Chicken. You take your chemical formula, you plug it into that equation, you will have the degrees of unsaturation. Do you notice there's a very common heteroatom that is not listed there? Oxygen does not impact the degrees of saturation. Halogens and nitrogens do impact how many hydrogens you would anticipate having. So we could plug this in for our equation up here, which is 2 times 3 minus 2, 4, 6 minus 0 halogens, 0 nitrogens, plus 2 divided by 2. 6 minus 6 is 0. 2 divided by 2 is 1. The chemical formula predicts 1 degree of unsaturation, and in this molecule it results from the 1 ring. So what then, if we take a molecule like pyridine? Pyridine looks like an aromatic ring, but it has a nitrogen inside of it. Before we plug in the chemical formula, count the number of pi bonds and the number of rings. What do you expect the degrees of unsaturation to be? How many pi bonds? 3. How many rings? 1. So this molecule should have 4 degrees of unsaturation. 8 additional atoms could be added. Let's plug it in. 2 times 1, 2, 3, 4, 5 minus 1, 2, 3, 4, 5 minus 0 halogens plus 1 nitrogen plus 2 divided by 2. So that gives me 10 minus 5 plus 3 divided by 2. 10 minus 5 is 5, plus 3 is 8, divided by 2. Chemical formula and analyzing the structure, they give you the same thing. If all you have is a chemical formula, you've got to do this. Is this the only structural isomer for that chemical formula? No. So this chemical formula is C5H5N, and I could have another compound that has that chemical formula as well. 1, 2, 3, 4 pi bonds, no rings, 4 degrees of unsaturation. Both of these compounds fit this chemical formula. So how would I know the difference? I'll take it to mass spec. They'll have the same chemical formula, the same molecular mass. I'll take it to IR. They've got different bonds inside of them. I'll take it to NMR. Their structural connectivity is very different. So degrees of unsaturation is the first step. Instrumentation helps us know what we're looking at. All right, I'll see you guys tomorrow when we dive into mass spec. Have a good night.